within 45 days. In addition to all that, my viewers can get 50% off their order. Like,
okay, you need to put yourself on mute.
the link is down below. I really encourage.
Good morning. My understanding is that Dr. Wahab asked to be removed as the instructor of record for this course, which is not unreasonable. And when this was done, you got denied access to Moodle. Dr. Gontier is working with university IT people to try and fix that. We hope to have it fixed today. Just in case it doesn't work, if you don't have a copy of problem set 8, which is due Wednesday, you can email Mohammed and he'll email one back for you. Okay. And when you go to hand it in, if we still don't have access to Moodle, then email it to Mohammed before 8:30 on Wednesday. I'm sorry that this happened. Personally, I would have just left the system alone because it was working, but that's hindsight, I guess. All right, with respect to last week, I think Brent, I didn't actually see what he did, but I've heard him in the past. I think he does a good job of showing you what engineering is really like. We had a couple of engineers from the oil and gas industry come and talk to you about a course, and they're trying to prepare you for the fact that there'll be a different language when you get out there from what you've had at universities. And moreover, sometimes when you get this language from people, they don't have it quite right, and so it takes a wee while to sort this out. But what you're going to do, and I appreciate the fact that they're trying to help you with that, though I would have to say I think it's perhaps a little wishful thinking. I've been consulting for 40 years, so quite often when I start a new case, I have stuff I don't know, and I have to go learn it. Okay, and that's what you sort of have to do. You want to recognize when you don't know something, and then go out and learn it. Talk to somebody who does know it, or find it out yourself. Okay. Well, we're going to return to this application we started the week before Brent gave his case study. Oh, and incidentally, the material in that case study is not on the final. Okay, so if you put a serious, significant effort into that case study, you will have learned quite a bit. If you didn't, you won't have learned much. But in either event, it won't be on the final. Okay. All right, we'll get back to bearing selection. It's a wee while since we did this. The first thing you do is you do the bearing dimensions. So normally when you're picking a bearing, you know the size of the shaft that you're going to mount with the bearing. So that gives you the diameter of the shaft, at least the part that you're going to put in the bearing. The shaft diameter may vary at other parts. Then you need to pick something, a bore diameter. Bore is the diameter of the inside of the bearing. Has to be smaller than the shaft, and it has to be smaller by the amount that's at least 2R. The most you can have is this R goes all the way up to the top, okay? And so you do this from table 40.1. Here's a bit of this table. So here's the bore of this bearing. Here's the shaft, okay? And here's this little R, which I drew a large version of. Let's say L means light capacity. 2 is medium light. Well, this is extra light, this is light, and this is light to medium. This first number and the basic bearing number decides the load capacity or groups the load capacity. The next number is the bore diameter divided by 5. Okay, so this is 25 millimeters, or about a 1-inch bore. And so this could take a shaft that the shaft diameter would have to be 25 plus 2 times 0.64, 1.2, so 27 millimeters or bigger, okay, to satisfy this. You could pick other shafts here, and you could pick smaller bearings, okay? Usually you want just a snug fit in here, and you tap it in and it fits. Sometimes you use a temperature a shrink fit, or you might put the shaft in dry ice and then stick it in there so it fits snugly. Okay, you want it to fit snugly because you want the bearing to adhere to the shaft, or at least the inner part in the race of the bearing has to adhere to the shaft. Once you've done that, then you need to get a bearing that has sufficient life for your application. I'm going to do a bit more on this today, but what we've got so far is you have a certain required capacity, loading capacity that your bearing must be able to take. And that's a standard radial load, or your radial load. The life you want over the standard life for CR to a power alpha. Alpha is 0.3 for roller, this alpha here, or it's 1/3 for a ball bearing. Here, CR, we'll see required. FR is the radial force that you've got in your application. You compute the life you want, typically in years, and you look at the RPM and figure out how many revs that means. That goes in here, okay? And as it gets bigger than this, it won't increase that rapidly because this power is less than 1, but nonetheless it will make the required capability for your bearing go up. And these are given in this table. We did a small example of this, but this is the bearing rated capacity C. The LR is 90 times 10 to the 6. That's the same as 9 times 10 to the 7. This is for a 90% reliability. I mean, when they generated this table, then 90% of the bearings were still going when it got to this life, okay? And 10% had failed, okay? This is the lowest reliability that you usually use for designing bearings. We'll increase that reliability, and there'll be a cost to doing that. You get a higher required capacity. Okay. In fact, that's the first thing we'll do. And so once you've computed, we did a small example, and I'll review that. Okay, compute your life, divide by the standard life, take it to this power, multiply by your radial load, and that's going to tell you what's required. And suppose you got an answer of 10, okay, then you could go look at and let's suppose 45 millimeters was your acceptable largest diameter. Then you wouldn't be able to use L or 200, but you could use 300. You could do 40 and you could do 300, and you could do 35 and you could do 300. But you couldn't, if 45 millimeters was the biggest bore you could have with the shaft you had, then you wouldn't be able to do extra light or light. You would have to do medium light, okay, when you pick off this list. Quite often when you get to this list, you get more options than one. Generally speaking, you pick the largest one, okay. But they're all acceptable answers. Let me talk about this reliability. So, you may well want a higher reliability. Now, one of the ways I've seen people do that is take two bearings and where one would do, and they both have 90%, then you sort of get to 99%, and when one of them goes, you can replace them one at a time. But there's other ways of doing this. So let me talk about that. There's a thing called a reliability factor. I can rework this and make it the life. Well, it's not, this has to be C, really. What's going to happen is this life is going to be reduced when you make the reliability higher. When FR equals C, this is 1, and you get LR, and that life then is for 90% reliability. As shown on the top of this list here. What we're going to do is we're going to change this L with a K with a KR. and KR was 1 for 90%. And so your life is going to go down when you ask for more reliability. The other way of looking at this is what's going to happen here. As this goes down, then the requirement for the load capacity is going to go up. This L would go in here, and here are values of this L. Get these from this figure 14, 13, okay? And for example, if you had 99%, well, here you can read this off at 90%, which is the minimum reliability, then it's 1. But if you wanted 99%, it's very close. About 0.2. So your life has gone down considerably, okay? For the given loads. We'll do an example using this factor and see what happens. It's not that unusual for people to want a greater reliability than 90%. There's another thing that happens with these bearings is you don't always just have pure radial loading. We're going to call this FT for thrust. So the radial loading as the name suggests, was out radially like this. Okay? It typically comes to things that are driving the shaft, like gears or pulleys. Axial loading, if we look sideways at this bearing, is along the axis of the shaft, which then, with the fitting I showed you initially, goes into the bearing. You really can't, well, it's a little bit dubious to use roller bearing. There's nothing set up to take it particularly. I would say at most 20%. And sometimes FT is 0. If you start to have some axial loading, you need to check with the manufacturer of the bearing to see what it'll take. The bearing I brought to school, now this bearing is made in India, and so the numbers don't match. The numbers I've been giving you are for US or European, but this thing here has no axial, can take no axial load, it just push it straight out. Okay, and so that's not that uncommon, but there are bearings where they have little racks inside, and the rollers can take a little bit of axial. Okay. So by and large, we typically use ball bearings to do this.
That expression is the thrust loading is less than or equal to the radial loading over 5, correct?
That's right. Less than 20. I'm not quite sure where I got that. I don't think that's in the book. But anyway, when you have relatively small thrust loading, maybe your roller can take it. But I'm telling you, what you want to do for this course is just assume FT equals 0 for roller bearings. When you're in practice, you might contact the manufacturer and see what sort of thrust loading his roller bearing will take. Okay, but it'll be modest. These thrust loadings can get quite big. So we're going to use ball bearings. And you can sort of see this. I doubt it will show, but these balls, which are separated, are inside a little, not quite semicircular, but a little dip in the outer race and the inner race. And so the ball themselves doesn't go in and out. And so this thing has some thrust capability. I'm pushing on it quite hard, and it's not giving. Okay? So what we do, then we will have a loss in life. So we're going to put the force up to an equivalent force, Fe, which is greater than or equal to Fr. If Ft is modest, less than 35%, then Fe just equals Fr. There's no effect. On the other hand, if you have high
does that mean FT is less than FR times 0.34, 0.35? I'm confused by that inequality.
Yeah, no, that's divide. Thank you. So Ft divided by Fr is 0.35, so it's less than 35%. Okay, or it's less than equal to 0.35, so less. Then you don't make it. On the other hand, when it's 10 times as big, then you take Fe equals 1 Ft, and now you're ignoring Fr. Okay. And there's a transition between these. That's given the equation 14.3. And I don't wish to write that out right now. We'll use this equation later, but I'll get rid of the book in a second. This is an expression here. When Ft upon Fr is 0.35, this will just give you Fr. This will be 1. When Ft upon Fr is 10, then this part here turns Fr into Ft, and it's multiplied by a number that's slightly bigger than 1.
What does Fe represent again?
Fe, that's a good question. Fe is the effective. Loading. So when you've got these expressions like this, you're going to put Fe in here for Fr. Okay. These are radial ball bearings. What I just did was radial. There are some thrust ball bearings. The way these ball bearings usually look is as follows. When they're angular, that's a radial. When they're angular, this side comes down, this goes up. And it can transmit more force as a result. There's an angle here, and the one you've been given is standard angle of 25 degrees. And so for this, instead of 35%, you can get FT up to 65%, and you don't have to change FR. FE is equal to FR. And when you get this very high loading, then FE is a bit lower. And in between, you use equation 14.4, which just looks like the previous equation. It'll give you these limiting values here. It's the same.
In the book,
Sorry?
it has FT over FR less than 0.68, I believe, not 0.65. Should we use 0.65?
No, you're quite right. I made a typo. Yep, that's 0.68. Yep, that's right. So not quite double what the radial bearing was. Now this thing here, you can do something like this with roller bearings too. Okay. Yeah, the only bearings we're going to use in this course are radial ball bearings, radial roller bearings, and axial ball bearings. Okay, that's all you need to worry about. But you can do things with radial ball bearings. Let's see if I can show you this. You can see that this thing here is sloped. Okay, and so when you put it in here, this will take the thrust loading one direction. Okay, if you push it the other way, it'll come straight out. And so there are, when you get on practice, there are ways you can get roller bearings to take thrust loading, but the straight roller bearing, basically, you're at risk. The ball bearings do a better job because of the constraint on the rolling path.
So in that case, why make roller bearings to bear a thrust load?
Some of these roller bearings can take very high thrust loads. Okay, yes, I mean, it's a fair question. I would say that this roller bearing, I don't know this for sure. I've tried to look these things up, but this is a Timken bearing. This is a Timken bearing. Okay, so this one I could look up, but this is made in Japan, so I don't really know what they can take, but this will beat this. Okay, and so it's an effective way of doing it. Why do that rather than an angular ball bearing? I think, I'm relying on the last time I worked on this bearing selection. I think this takes actually slightly higher thrust loading. Okay.
I can't see what you're using. It's not in the picture.
Sorry?
Your hands are not in the screen.
Oh, I'm sorry. Yeah. Okay. So this will take a slightly higher loading, I think. But so there will be some reasons why you would select this. Okay. Right. When you will do a problem, and you can see you wouldn't have to change your requirements too much to not have a radial angular bearing. You might be able to get a roller bearing and still get that in there and keep your friction down. Okay. Otherwise, then you're going to go to a journal bearing. But that's just my recollection. That this sort of bearing takes even higher axial loading than angular. But I'm not 100% sure of that. There's another thing that happens with these bearings. You try to avoid this, but you can have some impact loading. Now, when you think about your gearbox, impact forces, this should have been in machine design 1, impact force is V root MK. You might want to say delta V. It's a relative velocity between two bodies that hit. This is the mass involved and the stiffness, the mutual stiffness. The stiffer you make it, the higher force you get. The more mass involved, the higher force, but it goes as a square root. And when you have a difference in velocity, it's linearly proportional to that. This is the engineering formula. There's a better way of doing it than physicists who use momentum exchange, which might get you an average. Okay. So when you change gears, even with synchromesh, when the two gears come together, there'll be a slight difference. And so there'll be some slight loading there. Okay. Now, one of the things that's forgiving about that, the gear example, is that it only happens when you change gears. Once they're meshed, then there's practically zero sort of impact loading. Well, what we're going to do is we're going to account for this, we're going to increase FR by an impact factor. And if you have an equivalent FR, because of thrust loading, then we'll increase it by the same factor. To have no impact, then Ka is 1. If you have light impact, it gets up to about 1.5. And you get this from table.
What is the the light impact is greater than 1?
Yes, 1 to 1.5.
Okay.
And you get this from table 14.3. Let me show you this table. It's on the same page. Uniform load, no impact, then you don't have any factor, of course. Gearing with ball bearings 1 to 1.3, and for the roller, no significant effect. Okay. Light impact 1.2 to 1.5, so I should have put 1.2 here to be consistent with the book. And heavy impact 2 to 3, so a major increase for ball bearings, and a significant increase for roller bearings. Okay. What do you do when you're looking at this table and you've got this range? Well, in practice, you ask the question, how often does this impact occur? And if it occurs pretty much a significant fraction of the revolutions, what's a significant fraction? More than 10%, then you use the high end. Okay. If, on the other hand, it only occurs once when you start things up each day, then you use the low end. So that's in practice. What do you do in this course? You do the conservative thing. just take the highest value of each of these. Okay. Okay. So to summarize what we've just done, we have the following. Putting these things together. LR is this 9 times 10 to the 7th. We're going to have a reliability factor, KR. We'll have FE, which might still be just FR. And then we'll have an impact factor. And this will be to the 1 upon alpha. If you make C the subject of this formula, then you get FEKA. So you can see the impact factor is going to increase the required capacity. Okay. The thrust loading is going to make FR go up typically, so it's going to increase the required capacity. This KR, this reliability factor, is going to make this number bigger, so it's going to increase this, and this will be to the power alpha. So let me revisit the last example we did and put some of these factors in.
Dr. Sinclair.
Yes?
Where would vibrations fall into this?
Maybe, it's a good question.
The vibrations would probably just increase your loading.
Yes. It's unusual for vibrations to be an impact factor, but you could put it in as a light impact factor, I would think. Now, if the vibration, if the shaft is vibrating, it's hitting something, well then, of course, you're going to have a serious impact factor. That might even be high. Okay, but as long as it's not hitting anything, and it's, I don't think it has much of a factor. Okay.
Okay.
But I'm not. I'll think about that. Think about that. It's a good question. And you would go fix this thing, fix whatever your drive was and your shaft. If it started hitting things, that certainly would give you impact load. But normally the way you beat vibrations is you put extra bearings or something on it to change the frequency, so that the natural frequency of your drivetrain does not match that of the excitation, and that's how, if you've got excessive vibration, which may be in the audible range and therefore may be irritating. It also can increase, if the deflections start to be bigger, it can put extra bending stresses and it can reduce your life. And that is, as somebody suggested, you could go get your stresses from the vibration analysis and put that straight in to your FR, okay, which would go into the FE, okay, rather than impact. So I don't think you're really going to have an impact factor, but I'll think about it. we did this, it's been some time ago, so let me recap what we did here, and then we'll put in some of these factors and see what happens. Initially, we had the shaft diameter was 50 millimeters. FR was 1.2 kilonewtons. A kilonewton is about 220 pounds force, almost 5 kilonewtons to a kip. So it's a sizable force. It was going to run for 8 hours a day. It runs at 1800 RPM. $10 years. And what I didn't tell you is implicitly, we're going to take a reliability of 90%. Okay. And we had to pick a bearing. I did this before, so I'll just summarize what we got. From our table like this, I didn't print off the whole table. We went and found that if you had 50 millimeters, dB 45 plus 2R, whatever the R's were, I think they're about 1, was less than 50. So this would work. This was the biggest we could have. We could have something smaller than that. We converted this life. Okay, so we multiplied, this is revs, and we multiply minutes to per hour for 8 hours per day, the number of days into years, and you multiply all these things together, and you get 3.19 times 10 to the 9. So C required here would have been the 1.2 I've taken out a factor of 10 to the 7. And we were picking a ball bearing, I believe. Yes, we picked a ball bearing, I think. And we found that the required capacity when we did this calculation was 3.93. And I picked up a bearing from this table that did this. 45, all of these bearings are I'll move this under. All the 45s do it. So any of these would do it, okay? You could go down smaller. Eventually, when you get down to 30 millimeter bore diameter, the light one won't do it, but these two will, okay? And you can even go down further with the heavy duty down to, let's see, down to 20 millimeter bore diameter. So there's a bunch of bearings you could pick here. I picked the smallest, lightest one that was 45, the biggest bore diameter, but the lightest bearing, which is the smallest in terms of width, 5.8, and that beats that. Okay, so a number of bearings.
So which one should we choose?
Oh, well, actually, the way I did it is the normal practice. Okay, you in terms of giving an answer, any of these is acceptable. Okay, the normal thing is to pick your diameter to be as big as possible. Okay, that'll help the stresses in the shaft. Okay, if there's any stresses in particular. So the normal way is to pick this bore as big as possible because you're going to machine your shaft down. Plus, you don't when you make it smaller, you've got more machining to do. So you pick this normally as big as possible. Then you pick the smallest bearing because it costs less. Okay, and so this would be 45, and there'd be L, which is 5.8, which makes the speed. So the bearing number would be, you divide 45 by 9, sorry, by 5, would be LO9. But as far as you're concerned, if somebody asked you for an acceptable bearing, you picked anything below 3.93, that's okay. But I'd recommend this. Okay. Now let's give you some other factors here and see what happens to this. We're going to keep FR at 1.2, but we're going to add a thrust loading of 1.5. Significant thrust loading, comparable to the radial loading. We're going to want light to moderate impact. And we're going to ask for a 95% or higher reliability. And we're going to pick a radial ball bearing. So with these modifications, we need to compute the following. The required capacity, it's going to be FE, because this is clearly bigger than 35%. It's actually bigger than, FT is actually bigger than FR, so we're going to have an FE. We're going to have an impact factor. Then we're going to have L. LR is the standard. But now we're going to have a reliability factor, which will make it smaller. Make this number bigger, therefore, and it'll be to the 1/3. So we've got to go get FE. Well, we know what L is. L was as before. And we know what LR is. We've got to go get KR. We want 95%. So here's 90% KR is 1, 95%, that's between 0.6 and 0.7, looks like about 0.63 to me. That's all the things in here. KA. There's a bore bearing, okay. And we said light to moderate impact. Well, I think you would take the top end of light and the bottom end of moderate here. So if somebody tells you moderate to heavy, you take this midpoint. If they tell you heavy, you take 3, okay? If they tell you light to moderate, then you take the common point here, okay? If they just tell you light, you take 1.5. If they tell you moderate, you take 2.0. We always take the conservative, but light to moderate means we just take the common factor, the end point.
I have a quick question. Is there a difference between a radial bearing and a ball bearing?
Radial ball, the word radial, ball bearings, standard ball bearings are all radial, okay? The balls, the tracks are lined up like this. Well, my drawing leaves a bit to be desired, but, and so the axis of the ball here, where you bisect the little circular part it's sitting in, goes out in the radial direction. That's perfectly radial. And I tried to sketch it before. For an angular ball bearing, that little thing is off to the side like this. And so that's an angular ball bearing. It's still got a ball, but the line between the center of the receiving outer surface and the center of the receiving inner surface, that doesn't go straight out radially from the center of the bearing. It's off at an angle. So radial ball bearings are the standard ball bearings. They're usually just called ball bearings. When you talk about a ball bearing, you mean radial. That's what you say. Now we have to. Is that answer your question? Yeah. Okay.
Yes, thank you.
Okay. Now, so we've got this. Now we've got to go get FE. And I'll get that formula from the book, which I didn't write out before. It's quite lengthy. It's going to be between 0.35 and 10. So it's FR. Let me know if I make a mistake. This is because if and actually it's also less than 10, okay? But you can see when FT upon FR equals 0.35, this is 0, so you just get FE equals FR, just as we agreed. Actually, if you take FT upon FR equal to 10, and you put it in here, you will get the same thing as I gave you before, 1.1 something or other times FT. So we got to calculate this now. So I substitute numbers. 1.2 for FR. We said 1.5 for FT. At 1.25. About 0.9. This is very close to 1. There's going to be 2, so it's going to be about twice as big. 0.9 times 1. Yes, it's 1.003. So 2.4. So then the C required .4. That's for our FE. I'm doing this thing. KA 1.5. I've taken out a factor of 10 to the 7th, but this is times reliability factor 0.63. Well, that's obviously 3.6, but let's see what this is. $55.6. So previously, this is kilonewtons. Previously, when we did this with no modifications, we had 3.93. So this has gone up by a factor of more than 3. Now we go try and pick off an acceptable.
You have 315 over 9 times 0.63?
Yes.
Isn't it 3.19? Shouldn't it be?
Oh, sorry. Did I miscopy that? Oh, yes, it should be 3.19. So this will be slightly bigger. Yes. Okay.
I think it only brings it up to 13.8, but
Okay. Okay, so this will be a little bit bigger. So yes. Thank you. Okay. So now we go look for 45 as our minimum. This is still the biggest bore we can have is 45. And we find that we can't use, let me slide this up, 40. We can't use an extra light or light 200 series, but we can get by with 300. So the right bearing here is the 300. And you divide 45 by 5, so it's 309 is the bearing. And now, because of the, I'll undercover that in just a second. Because of all these other factors, that's the only bearing. That is the only bearing that'll do it, okay? So, and this is somewhat representative of the sort of extra factors you do get, okay? All right, well, I'll think about what happens when we do an angular board. Well, let's take a break for 5 minutes. Any questions on that? Thank you for correcting that. I don't mean to make a mistake, third figure, but yeah, I had 3.19 before. I'm pretty sure that I copied that from my notes previously, so I think that's right. So as you get more of these factors, higher reliability and so on, then it gets harder to find the bearing. Okay? The bearings that are available tend to be the ones that are the largest possible. Okay? And occasionally you might use something smaller. And when you get off this list, then the next thing you go to would be angular. Okay? And there would be a further chart here for angled roller bearings, which we don't have. They're less common, but we don't have them. And you might be able to do with that. Okay, let's take a break for 5 minutes. Unless there are any questions. Okay, well, we make a further comment on this modified example 30. Let's suppose we chose instead an angular ball bearing. Well, this KR, this reliability factor for 95%, that independent of whether it's radial or angular, it comes from the same chart, okay? So it doesn't happen. And KA comes from the same table, and it just distinguishes between ball and roller bearings, but it doesn't distinguish between angular or radial ball bearings. So since we said light to moderate, then we picked the common point between the two. That's unchanged, but this FE changes. So now we get the formula. And the formula used to be FR was formula here. Now the formula is and 40.4. This coefficient is different. It's reduced. It's going to give us lower FEs from 870. And now instead of being minus 0.35, it's minus 0.68. And this formula holds for FT upon FR from 0.68 to 10. Above 10, you just take the formula that's given in this equation, incidentally, that I gave you earlier. And you'll get the same value if you put it in here, but you don't keep using this formula when you get above 10. And you don't use it when you get below 0.68. At 0.68, this will be 0, so you just get FE with FR.
Are all of these angular ball bearings going to be at 25 degrees,
Yeah.
or is this only valid for the ones that are 25 degrees?
Oh, this is the most, there are other angular ball bearings, but this is a very common angular ball bearing. This is the one, as far as you're concerned, is the only one you need to worry about. Okay? There are some other angular ball bearings. Okay. So if we compute this now, 1.2, It's turned out to be 1.8 basically. It used to be 2.4. So what's going to happen is C required is going to go down. C required has FE out here in front. We just reduced FE by 25%. $10.4. Let me just put the office light back on. So now when we go to our table, 45 millimeter bore is still the biggest bore we could have. We can't go higher than that. But we went 10.4. Actually, the 200 would do it. Right? It's right at it. Okay. And the 16 and the 300 would do it. We'd have two. But we have another two 300 level bore bearings with a smaller bore that would also work. 13.2, 11.0. So there's a number of bearings. Which would you pick? I would pick the one that's got the biggest diameter. Okay, that'd be 45. And so then I would think that the 10.4 is a little close. So I would go for the 300, but it would be a correct answer to use the 200. So I would say 209 or 309 are good choices. But you have multiple choices. So the angular ball bearing lets you have more options. But you can still get off this page, okay? And that means you're not looking about to use one of these ball bearings. That can happen. Well, that's about all we're going to do on bearing selection. I'm going to move on to the next application. Do you have any questions before we move to gears? Okay. What a lot of this sort of stuff is in practice is there's lots of looking up at tables to get the things that you want. Okay. All right, well, the next application I'm going to look at is Spur Gears. And this is in Juvenile and Marshak, chapter 15. What are we talking about? Something like this, okay? These little spurs come out here. They're uniformly spaced around here, and you mesh this with another one, typically of a different diameter. And so what we're going to have here I'm not going to bother drawing all the teeth or spurs. Although we'll look at this in a little more detail in a moment. You typically have a different size between two meshing gears. In which case, the bigger one has DG, pitch diameter. And the G stands for gear. It's common to call the larger one the gear. The smaller one is the pitch, is the pinion. If they're both equal, they're both gears. Okay. Well, you'd have them both equal when you're trying to shift the line of rotation laterally without changing the speed. And if we look at this in a little more detail, there's the following. Let's see if I can get this from here. Okay, so these things are curved shapes like this. There's a little radius there, okay? Then there's a pitch point here, which you can think is, there's more than one definition of it, but as the point of contact. Well, contact actually moves up and down along this. We'll talk about that in a little more detail subsequently. But this is perhaps the mean point of contact you could pick out. Then the pitch is the distance from this point on this tooth to the same point on the next tooth. This out to this point here, to the center of the gear. DG or DP upon 2, okay? So if we take the entire circumference of the circle of radius d upon 2, then its circumference would be pi d, and that'll be NP. Oops. Number of teeth. Okay. So that means a D, or P rather. So for the gear I had here, D is about 4.5 inches. I counted in before class, there are 30 teeth. So P .47 inches, nearly half an inch. It's a large gear. You can get smaller P than this. There's another pitch which is used. This pitch here P can be in millimeters or inches. In the US, it's typically inches. In Europe, millimeters. Yes, I use. So that's changing. But a common alternative definition, which is essentially equivalent, but you're going to meet this, it's called the diametral pitch. I'm going to use the same symbol as the book, P. P is used for a lot of things. Okay. But anyway, P and units are teeth per inch. Okay. Well, we can solve these two for n. P, uppercase P. It's also n is lowercase p. So these two just equal a number p. You lose the inches. So if they give you this, you can convert it to this if you need to. You may well not need to. Independent of which pitch you use, here's the requirement for meshing. That physically the separation between the teeth has to match. And I have this little figure here. When you're bringing in another gear, then this distance here has to match. Okay? That's sort of why I prefer this, but you can get the same result here. That means that dg upon ng equals dp on np, where this is the number of teeth in the gear, the number of teeth in the pinion. This would be bigger than this, as with dp. The angular velocity of these, you have a common velocity at the pitch point, which is where we measured the pitch at the time. And so that common velocity would be v of the pitch point, and that would be omega g dg upon 2. And it would, the velocity here, it's actually in the opposite direction, minus omega. Like, so this point has a common velocity v. If we say omega is positive clockwise, then this one's turning counterclockwise. You get a minus minus, and you get the same v. Okay. So what we're going to have then is, for meshing, omega g, it's going to be d and these d's were inversely proportional to n. Right. Did I get this right? Half a second. It's going to be NP.
It should be
Oh.
NP
Oh,
over
yes,
NG.
yeah, yes. I'm sorry. D is. I was looking at this formula, looking at P. D is directly proportional to N. Yeah, I was about to write down something that didn't make any sense. Okay, okay, that's fine. If you have an even number of gears, 1, 2, or 4 in a line like this, then you'll get a change in sign of omega. Okay. So if I had 2, then you get a change. If I had 4, another 2 here, then there'd be a change in sign here, another change in sign, then a third change in sign, so it'll be a change in sign. On the other hand, if you have an odd number, then now it's going the same way. It started off clockwise, counterclockwise, clockwise.
Dr. Sinclair.
Yeah.
Wouldn't it be the other way around?
No.
Sorry, go ahead.
So here, this is an even number, 2 gears, right? So this is going clockwise, okay? This one's going the same direction at this point here, and so that's counterclockwise. So you've got a change of sign in omega, okay? If you say omega is positive, it's clockwise, then this omega here is negative.
Yeah, but you're saying even number of gears changes sign. Okay, I see what you mean.
Yeah, and so if okay, all right. So here I do.
I got you. You don't have to draw it. I got you.
Yeah.
I didn't hear this the other day. Sorry to cut you off. It's my bad.
Okay, so this here, this would be up. Let's see, this would be up. Yeah, there's still a change of sign, right? This is still going down. Okay, there's a change. This one here is going the same as this, so there's an odd number, 3. Okay.
Dr. Sinclair,
Yep.
on the previous page,
Yep.
on the expression you had for meshing, you had P subscript, subscript G equals P subscript D.
Yes.
Did you mean for that to be P subscript P for pinion?
Oh, yes. Yes. I can tell you why. More often than not, you drive in the pinion, so you call it a D, but no, that's to be consistent with what I did. You're quite right. It should be P. Yes. Okay. So quite often the incoming drive is from a pinion, and so sometimes you put a piece of D, but I hadn't done that. What I did was incorrect. You're quite right. There are gear forces. If time permits, we'll deal with these a little bit more because these are going to have bearings on life. I tried to draw that tooth using the actual gear. It's got a shape like this. The resultant force is not normal to the radius. Okay, and so there's a radial force and a tangential force. And these are on it when you mesh your teeth, you have essentially contact on one set of teeth, one from the pinion and one from the gear. Okay, and then when that starts to cease, then and the contact starts with another tooth. That's not 100% correct, but it's pretty close. And these two are related by a pressure angle. And as you shape the tooth, you get different pressure angles. And this course we'll use two, most common. (20, 25 degrees. So if you take a tan of 20 degrees, that's about 36, 46. So this radial force is not an insignificant. It's at about 26 to 47% of the tangential force. So this thing is off at an angle here. However, when it comes to power, and you get that from torque, and the torque is all generated by Ft. Well, now I'm going to put a hat on power just to distinguish it from this other pitch, the diametral pitch. So it's going to wear a hat. And that's just T omega. Okay. Power is force times velocity, or in an angular situation, it's torque times angular velocity. And T is going to be driven by this Ft. It's going to be Ft times the radius. Okay. You can turn this around and you can get this tangential force from the torque you're transmitting. One last element of these introductory notions about gears, let's talk about efficiency for spur gears. Here's the power you get out. Divided by the power you put in.
What are you watching? An influencer video?
Sorry? What was that?
Easy. Yeah.
So we can turn that around. Oh, let me give you a range. E is pretty good for spur gears. This is because the shape of these gears have been carefully engineered. So there's very little of any relative lateral motion in contact. So there's very little in the way of friction losses. If we use this efficiency, we can use this. That's going to be the output torque times the output angular velocity. And likewise, there's the input torque So therefore the efficiency or you could make the output torque, which is what you often want, is going to be the efficiency times TI times omega I over omega 0. Just to get the magnitude, we can switch these up inversely proportional to the number of teeth. I'm not keeping the sign here, okay? In over in I. So it's magnitude only. These torques are going to change direction just like the way omega did. So to summarize what we've covered so far, we have the following for Spur Gears. And I'll do an example. That's the pitch, which is the physical dimension between two teeth. Here is the common diametral pitch used in the US.
What is your sign convention that you typically use for?
Oh, it really doesn't matter as long as you declare it, okay? And so you're going to be given, say, an input to a shaft and you're told it's RPM, then what you want to know is the output shaft spinning the same direction or the opposite direction, okay? And that's a matter of tracking the direction changes. I'll think about that too. Yeah, I'll think about that. Okay. For meshing, this has to be the same, or this has to be the same as you go. Okay. This to me is more obvious in this physical dimension. Angular velocities with one pair of gears, you get a sign change. And they're inversely proportional to the number of teeth. Okay. This is G upon P, this is P upon G, that's not a mistake in sign, it's just for one pair of gears. If you get enough of these signs, they're an even number, of course, then you won't be any change. When we start to design bearings for these gears, shafts, then we'll need to start computing these forces and getting resultant forces. T is really due, the T that creates the power is really due to the tangential component of the force. Efficiency is the power you get out from the power you put in, less than one, but not that much less. This is magnitude. Well, let me do an example of use for you. Let me show you what I mean by reduction gear set, though there's more than one of these. So I'm going to drive this pinion with a motor. There's 3 shafts here. Just to keep things simple, I'm going to keep, which will help line these axes up. Okay, so it's not just moot, but I'm going to make this the pinion, this a gear. I'll make this the same pinion, this the same gear. Now there'll be a sign change in omega here, and that'll be reversed back here. So this is going to spin, the output here is going to spin in the same direction. This is not in defiance of what I said earlier about an even number. It's an even number in a set of gears all joined, okay? This is 2 sets, okay? And there's a change of sign here and a second change of sign here. So this thing here is spinning the same way. Of course, as this does a revolution, the small gear, this one only does a part of a revolution. And then as this small gear does a revolution, this thing does only as part of a small. And so that's why it's called a reduction. The speed goes down. Okay. What will happen then is if we'll lose some power because of efficiency, but then the torque will go up. So when you have a reduction gear set, it's common practice, you have a high revving motor, the revs will go down, the output revs will be lower, but the output torque will be higher. Here's some specifics for this gear set. The pinions give me a US unit P equals 5. The number of teeth is 15, and phi is 25 degrees. Since you're going to mesh this, then you don't really need to write this, but P will again be 5, and phi will be 25. Okay. Otherwise, you will have poor meshing. Well, in fact, you won't mesh. But N is 45. I'm going to use SI units for this. This happens all the time with gear problems when you start using US units and SI units. you get a mixture of the same problem. So PI is 1 kilowatt. And at 1200 RPM. Okay. I would like to find out what the output is from shaft C. Okay. So what we've got to do is get a little shopping list of things we have to do here. What we see, well, part of the output will be what's its omega. And to get that, we're going to have to get omega for B and C. Then if we want to talk about output, we want to know what torque is. We'll have to get that for A too. And we want to get the power that came out. At least in this first exercise. So for A, this is a G, this is opinion. It's minus NP over NG. So omega B, which is the gear, equals omega A this was 1200 RPM, which is a standard unit to give angular velocities and for gears. When we start to work out power, we're going to have to convert from RPM to radians per second. But when you're talking about output, then RPM is the standard thing. The minus sign means in the opposite direction. I gave this direction, but irrespective of whichever direction I gave here, this is the opposite. And this is NP, there's the number of teeth in the pinion, over the number in the gear is 45. This is minus 400. Likewise, omega C, it's the same arrangement. It's minus omega B times NP over NG. So you'd reduce this again. And 400, 133 divided by 3. And now, to answer your question, the key thing is this is the same direction as A. We get T, and the 1 kilowatt, which is 1,000 watts, and a watt's a Newton meter per second. And now omega has to be in radians per second. So we're going to get the torque out in Newton meters. We've got 1200 RPM. We have to convert that to radians, 2 pi per revolution per second. .96 Newton meters. Now what's going to happen is TO for a given gear pair is E, the efficiency for that gear pair, times TI. The efficiency we're given was 95%, so this would be TB. This would be TA. This is the number of teeth, and B, 45. So there's a bit of a loss for the efficiency, but nonetheless, it's approximately 3 times bigger.
Dr. Sinclair?
Yes?
Could you move the paper left a little bit? It's getting a little hard to see.
Sorry.
Thank you.
TC is the same thing. Again, it's 0.95. Now it's TB. We have the same ratio. .6. Hasn't quite gone up by a factor of 9 because of the efficiency, but close. And so to complete the power then, C sorry. P out. This is going to be the 64.6 times omega C. Omega C was 133, and now that's RPM, so it's times 2 pi over 60 to get radians per second. And this will be in watts. I get basically 900 watts. W, which is about what you'd expect. There's a little bit of round off in this number, I think. Yeah, that'd be 902. Okay. So you could get this power just by taking the power in and multiplying by E to the number of gear pairs you have. Okay. Well, we'll do a bit more of this. One of the things you'd have in a set like this that you'd have to design, but you have to design bearings for this shaft, and this shaft, and so on. And these bearings are going to experience the radial and tangential forces that are going to come in and give you a resultant force on the bearing, which you'd have to design for. That'll be a radial force on the bearing, okay? Even though it'll be a combination of both forces, a resultant force on the gear. And we'll perhaps do that next time. Are there any questions on that? So just sort of recapping here. Sorry if I'm running a little bit late here, but this is the basic things that's happening here. When you have gear angular velocity, they're inversely proportional to their number of teeth. Okay, this is ng upon omega g upon omega p. This is np upon ng. Okay? Don't put the g here and the p there. Okay? And you get this minus sign. And then power is just torque times omega. Torque is given by the tangential force. Okay? And what you're going to do to get output torque is you're going to take charge of the efficiency, and then it's going to go as NO over NI. Okay? That's what the output torque is. That's what happened here. There's more than one way of getting this answer. We could do it this way or this way. Okay? But they should be consistent. Are there any questions on that? That was a wee bit hurried at the end there, but I think that's a pretty simple example. We'll perhaps come back and design bearings for this. Okay, if there's no questions.
In part A, getting omega C, you said negative omega B. I'm just making sure, I couldn't read it very well.
Yeah, yes, omega C is minus omega B.
Okay.
And omega B was minus, so the two minuses make a plus. Okay?
Okay.
And if you, I don't know, what I tend to do in these is I draw the way these things go myself. So that's clockwise, so you can see it immediately. But you can carry it with the sign conventions, and I'll think about whether there's a preferred sign convention or not. Most people, if they're analyzing a gear set like this, will just tell you the input is such and such, so much horsepower, so much RPM, and the output is such and such at certain horsepower at a certain RPM, and you say same direction or opposite. Okay. Reduction sets like this always reduce things at the same direction. This is a common reduction set. You can just have two in a reduction set. When you have two, then of course you've shifted your shaft where your shaft is, and quite often you want to maintain your shaft. Okay. If you think about your drive shaft down the center of the car, it goes through a gearbox. It comes in at one point to the gearbox and comes out at exactly the same point. Okay, comes in from the engine and goes to the rear, typically the rear wheels. Okay, and that's lined up. And so you have gear sets like this within that gearbox, which don't end up shifting the input shaft line of action. Any other questions?
I have a question about the Moodle for this class. We haven't been able to see it since about Wednesday, and I wasn't sure if there's something that needs to be done on our part or whatnot.
Okay. Well, I talked about that at the beginning of class. Maybe you missed it, but Professor Gontier is talking to IT people trying to get that fixed today. And hopefully we'll get it fixed. If when you go to hand in problem set 8, if Moodle's not working for you either on Tuesday night or Wednesday morning, you can email it to Mohammed Islam. Okay. And if you haven't got a copy of problem set 8 yet, then you can email him and request a copy. He has problem set 8. He can send you a copy.
Okay, thank you, sir. I'm sorry about coming in late. We had a quiz this morning.
Oh, that's okay. Yeah, you know, I'm sorry about the mess. Okay, I really couldn't care who's listed on the Moodle page as the instructor. But I think, to be fair to Dr. Wahab, I think he had intentions of coming back and teaching this class after a couple of weeks, but after a couple of weeks, he just wasn't well enough. And so that didn't happen. And perhaps we should have. But I think we probably would have had a mess like this whenever we did it. And it's a bit unfortunate for Brent, who's a good fellow. And in fact, let me comment that if under these circumstances, if you thought we've got quite a bit out of his presentation, you might send him an email and thank him. That would be nice thing to do. When he does this, there's no charge to the department, and he's an experienced, good guy. So it's a nice thing to do. Anything else?
I have a question regarding like grades and stuff. So are you trying to get the same Moodle page back up so all of our progress and stuff will be saved, or is it going to be like a new Moodle page?
Oh, we haven't lost that stuff. It's just a matter of you don't have access to it. So we will use all that stuff. Okay.
Okay.
There haven't been any projects, but I mean, but we'll have your homework. We have your homework grades. Okay. So So and we have all your test grades. So none of that's lost. Now, rating for last week, I'm not quite sure about what we're going to do about that, but nobody will suffer because you lost Moogle. Okay. Maybe what we'll do is we'll just get rid of those homework problems anyway, because they won't be on the final. But
Dr. Sinclair.
Yes.
This is MD. This is Mohammed. I just checked the Moodle page and I saw all the names in the new Moodle page, and it's on your name. It's 2021 Spring ME 4244 for for Glenn Sinclair.
Okay.
And I saw all the students are in that list. But
Okay,
I'm
it's
not
working
sure.
for me now.
Yeah, it's up for me.
I see it too.
And
Yeah,
everything's there too.
Okay.
Yeah, I think you all
we can
students
just,
can submit the homework and everything here. And I think even the lecture video and all the links are available here. Okay.
That's good. That's good.
Sweet,
We're
thanks,
hoping to
Andy.
get this done today, but that's real good. Okay. Sorry about that mess though. Okay.
Okay. Bye.
Thank you.